All right, everybody, welcome back to the third installment for rotational motion. And for this video, I'm just going to be working through some problems. The last two videos were dedicated to sort of laying out all the concepts there, but this will help both do that, talking about the concepts with the problems and actually doing some problems that might show up with some kinds of questions on the AP test. So first off here, we've got an 8.2 kilogram mass and a 12 kilogram mass on opposite sides of a fulcrum. It's a seesaw, essentially. We've got this board, and the board has negligible mass. There's not enough mass in the board for it to matter. And it tells us, and it gives us this nice diagram, the 8.2 kilogram mass is 4 meters from the fulcrum, but the distance to the 12 kilogram mass is unknown. And at this point, it doesn't really say it might be a little bit clear. It is balanced. So this board is not rotating, and because it's not rotating, that means that the net torque on it must be equal to 0. So whatever torque is being applied by this mass, so this torque in the clockwise, we also have a counterclockwise torque, CCW, and those have to be equal because when those torques get balanced out, they have to equal 0. So I can say now that the torque in the counterclockwise, we say those are positive torques, minus the torque in the clockwise must equal 0. So a torque is a force. So the force on both of these is mg. Just like it would have been before. It's the force of gravity pulling both of those down and causing that torque. So I will say that the counterclockwise ones, this one on the left, the 12 kilogram, would be 12 times 10, so mg. The distance out, that's that x value, because a torque is a force times a distance away from the axis of rotation, which in this case is that centerpiece, minus 8.2. Again, times 10, that's the mg, but this time we know it's 4 meters. And I'm leaving out the sign of the angle because in both of these cases, we've got a 90-degree angle. If you take the lever arm with the direction of the force, that's a 90-degree angle. So that comes out to be 1. I'm not going to include it. It just sort of muddies up what we're looking at. But just be aware that if somehow we had a different force, something pushing at an angle, a further problem will have that. But we don't got to worry about it right now. And both of those have to equal 0 when we subtract those from each other. So I'm going to clear out some of this so I can write again. But what we're going to end up with is 120x equals 8.82 times 4, which is 248. Just kidding. 328. So when we divide 328 divided by that 120, we should get an x equal to 2.73 meters. So we just divide 320 by 120, and that gives us 328. So then with that value in mind, it says what is the torque created by the 8.2 kilogram mass. Well, now we're going to do the exact same thing, but we're only worried about that one torque, and now we've got that. The torque of the 8.2 is the mass of it. Oh, by the 8.2, we've already done most of this. 8.2 kilograms times 10 for the G, and then we also have times 4. And again, it would be the sine of 90, but that's just 1. So our torque is going to end up being, let's see, it is 328, we just said that. And torques are newtons times meters. They are newton meters for torques as the unit. So then the question is, what upwards force must be generated by the fulcrum? So this is where we actually sort of switch over to just regular net force. And because this object is not actually lifting up off the ground at all, or it's not falling down, our net force, like our torque, also has to be 0. So now, instead of worrying about the torques, we just want the forces up and down. So we're going to have some positive force by the fulcrum, that's the little triangle guy in the middle, minus the weight of the first mass minus the weight of the second mass, and that must equal 0. So the force of the fulcrum, let's see, we've got an 8.2 and a 12 kilogram mass here. So force of the fulcrum, and I'm going to add both of these over to the other side. So the force of the fulcrum is actually equal to 8.2 times 10 plus 12 times 10. So 120 plus 82 should be 202 newtons upward. 202 newtons upward. And which of any of these answers would be affected by moving the whole system to Mars? The only ones that are going to do that are going to be B and C, because those are the only two that actually involved gravity. So the value of X, regardless of what planet we're on, because both of those torques were affected by gravity in the same way, if we change it, it affects them the same way, and we end up needing the same distance. But when we're talking about specifics, the torque created by this one is changed if we change the gravity, and the same is true of the force that needs to be applied upward by that fulcrum. It will actually be less on Mars. The gravity on Mars is actually a little bit less than it is on Earth. Number 3, similar situation, but this time it tells us that we've got an 8-meter long board and that we've got a fulcrum supporting a board, and the board actually has a mass of 5 kilograms this time as well. So this changes things just a little bit. So let me change this up a little bit. One of the things we can do is actually take this board, and this is where it gets a little interesting because this board actually has mass. And if we're talking about a board, something flat like this where it's all sort of uniformly distributed, we can actually say that that 5 kilograms really rests right in the middle. So if this is an 8-meter board, that means that this guy from the center to there is 4 meters. We know that that 5 kilogram mass has got to be 4 meters, a sort of centralized 4 meters away from there. Okay, and so what is the value of X then? We need to balance all our torques again. So our torques that are clockwise equal our torques that are counterclockwise. So in this case, I've got one torque that is counterclockwise, and both of these torques, I can actually have the whole board again sort of housed in that place. That will be a torque downward, and downward in the clockwise direction. If we sort of follow those along, both of them would be clockwise. So I'm going to have one torque that is clockwise, the others that are counterclockwise. So I'm sorry, vice versa. So I've got the 12 times 10, so that's the mg, and then the distance, that is x, and that is equal to that. And then those will be equal to the 8.2 times 10. And the distance away from this fulcrum, the distance from that center of rotation there, is going to be total distance minus x. So it will be 8 minus x here. And then along with that, I've got another clockwise. I've got the 5 times 10 times this time. We know that this whole distance here is 4 meters because we said that the center was at 4 meters. So the only distance I'm looking for here is going to be 4 minus x for that distance away from the center of rotation. So doing all of that math, we end up with an x of 3.4 meters. So we have 120x equals a bunch of other goodies as well. Let's see if I can clean some of this up. Ends up being 20. Yeah. Forget it. I'm trying to do all that math out. I did it earlier, but writing it out, again, that is just algebra. You should be pretty confident there. Upwards force generated by that fulcrum. This time again, we just have to sort of balance these forces downward. We've got 120. Clear that off. 120 newtons down. We said the board is 5 kilograms, so that's 50 newtons down. 82 newtons down, which means that if it's not going to accelerate up or down, this fulcrum has to push up with the sum of all those. So 202 plus 50, so 252 newtons there for our force. Problem 3 says, what would happen to the size of X if the mass of the board was increased? So if I increase the mass of this board, and let's say that this was, I don't know, 6 kilograms now, I would have more of a force, more of a torque pushing this way. I would have more torque pushing that way, so I would actually need to shift over my X. It would get greater. If I increase the mass of the board, it would shift the extra torque to the right side, so there's more torque over here now. So in order to balance that, I need more torque coming out of this force. I can't change the force, I'm not changing the mass, but if I make this X bigger, that gets me more torque. And I actually make these two torques smaller over on the right side as well. So X would have to increase to move the fulcrum towards the right to make those torques remain balanced. Number 4, kind of a setup here. Let's say that the Joker ties Batman to a conveyor belt, as you do, and we have a saw blade that can be thought of a disc, uniform disc, with a radius of 1.4 meters. I'm actually delete this so I can use it. There we go. Uniform disc, radius 1.4 meters and 38 kilograms. The edge of the blade is moving at a tangential velocity of 80 meters per second. So if I took a point anywhere on the edge, it would be moving with a velocity of 80 meters per second. Okay? First question was the angular velocity of the blade. We can actually convert angular velocity and tangential velocity. So the tangential velocity is equal to the angular velocity times r. And that actually puts it in radians per second. So my tangential velocity was 80 meters per second. W, the radius it says is 1.4 meters. So if you take 80 divided by 1.4, that should end up getting you 57 radians per second. Then it just wants a conversion to get into revolutions per minute. So I'm going to take 57 radians per second. I know that I've got to get it into revolutions per minute. So I'm going to convert my radians first. There are 2 pi radians in 1 revolution. So that means that my radians cancel out. And then I need one more little conversion. I've got 60 seconds in 1 minute. My seconds cancel. I am now in revolutions per minute, and when you multiply all of that goodness out, it ends up being 546 RPMs, or revolutions per minute. Not too terribly fast, but not too slow either. It's about 10 per second, 10 revolutions per second. For C, it says Batman works loose hand, checks a battering at the stop button for the blade. The blade takes 12 seconds to stop moving while accelerating at a uniform rate. What angular acceleration did the blade experience? So, angular acceleration is a change in angular velocity over a change in time. So it tells us that the change of time was 12 seconds. It took 12 seconds for it to slow down. And I needed to go from the angular velocity, which we said was 57, to 0. So we have a final of 0 minus the initial of 57 radians per second. And if we do that, it should end up being negative 4.76 radians per second squared. Put the negative there because it is moving in the opposite direction. I picked for the direction it was being moved at to be positive, and because it's slowing down, it has to be accelerating in the opposite direction. Letter D, through what angle did the blade rotate in this time? This is where we actually get into the kinematics type problems here. So it's asking about the angle. I'm going to say that delta theta equals the angular velocity initial times time plus 1/2 angular acceleration times time squared. I'm looking for the angle it went through. My initial speed was 57 radians per second. The time it took was 12 seconds plus 1/2. My acceleration, we said, was the negative 4.76, and this is where the negative becomes important. If I put positive, that means I'm speeding up, and I'll get the wrong answer here in this situation. Again, the time is 12 seconds, so we'll square it. Doing that algebra out, I ended up with an angle of 343 radians. And again, because I use radians per second here, I end up with an answer of radians. If all of my units had been maybe revolutions, I had revolutions per second squared and I had revolutions per second, this answer would come out at the end in revolutions. As long as you keep all of your units the same, you're good. But make sure that the acceleration is the same unit and the velocity is the same unit, using the same measure of angle for all of them. Got a problem about Superman now. And it says, let's see, flies into one of the largest gears and exerts a force, we'll call it Fs, to attempt to turn the gear as shown in the diagram down below. I'll scroll to that in a minute. His force is 3 meters from the axis of rotation at a 75-degree angle. So now, in this problem, we are going to have to do that sine of the angle when we worry about our torque. He's not applying it at a direct angle. Radius of the wheel is 5 meters and has a total mass of 800 kilograms. It can be thought of as a thin hoop. We are not going to have to worry about that. We'll sort of skip that piece of the problem. Again, it's not something that gets stressed on the AP test. Another gear exerts a force of 1,200 newtons and a friction can generate a maximum force of 3,000 newtons as shown in the diagram. So really, we're worried about the diagram here. So it says, what force must Superman exert to rotate the gear at a constant angular velocity? If we have a constant velocity, that means that our acceleration has got to be 0. And if our acceleration is 0, and in this case angular acceleration, that means that the net torque also has to be 0. That is a concept that you should know. Make sure that if you're not accelerating, there is no net force. There can be individual forces like we see here, but we do not have a net. So again, our net torque has to be 0 in this case. It doesn't matter that it's rotating at that 1 radian per second. That is a velocity. It's constant. There's no acceleration. So for this one, I need to get all of my torques to balance. This FG is pushing the object that way. It's causing it to rotate clockwise. So I will say FG plus the force of friction is doing the same thing. It's pushing it clockwise. So the force of friction, those have to equal the force that Superman is exerting in the opposite direction. So I'll put Fs. And I should really not even say force. All of those should really be torques. We're worried about torque here, not necessarily just force. So I'll rewrite that here. So the torque from G plus the torque from friction equals the Superman torque. So the torque of G, it says it's a 1,200 Newton force. I'm sorry, 12,000 Newton force. And it is, let's see how far away it says. Radius of the wheel is 5 meters. So that force is being applied 5 meters away. So I will apply it here. And this one is at a right angle, so it would be the sine of 90, which is 1. I'll leave it out. Plus the force of friction, same thing. It is being applied at the axis, I'm sorry, not at the axis, at the radius, so it will be 3,000 again times 5. But then we've got this force of Superman that we don't actually know what the force is, but we know from up above in the problem that he is exerting that force 3 meters away, and he is doing it at an angle of 75 degrees. So instead of being at 90, he's at 75 degrees. So not quite as efficient. For two reasons. Number one, his angle is lower than 90, which means not all of that force really gets used as a torque. Some of it is not perpendicular. And he's closer in. So because he's closer in, that force is not as good as at causing an angular acceleration. So if we work out all of that math, again, at this point, it's just algebra. The answer should come out to be 25,900 newtons. So he had to exert a significantly more, a greater force than just 12,000 plus 3,000 because he was closer in and exerting it at an angle. What force must he exert to rotate the gear so that it accelerates at a constant 2 radians per second? We're just going to rework this a little bit. We're going to say that all of these forces added up, and I'll put his first. So I'll say the force of Superman, or I'm sorry, all of the torques added up times 3 times the sine of 75. The force of friction, that friction torque is acting in an opposite direction, so I'll put it negative. Same is true for this force G is also 5. And because net torque equals I alpha, I, and then the alpha, it wanted for 2 radians per second. Now, in past years, there has been some work done to talk about how we actually calculate that I value. But again, the AP test has shown that it doesn't require that, that you do not actually have to know how to calculate that. So in this case, let me just check my notes here. Equals I alpha. It is 8 times that, which ends up being 40,000. This whole side ends up being 40,000. But again, we are balancing torques. We're using net torque equals I alpha. That equation basically tells you how much force and how much torque has to be applied to get a certain acceleration. Work it all out, and the force itself, just that force of Superman, is 39,700 newtons. Down to letter C. Here we've got a problem where it says if the gear starts at rest and accelerates at a constant 2 radians per second, how long will it take to rotate through 4 rotations to be fully open? I'm going to go ahead and convert my rotations into radians. So 4 rotations, and I get 1 rotation for 2 pi radians. So I end up with a angular displacement of 8 pi radians. I like to start there. I like to get all of my units using the same value for the angular displacement in radians. So I've got 8 pi radians as my delta theta. So I need an equation that can relate me time, acceleration or angular acceleration, angular speed, and angular displacement. This is just a kinematics problem. So I'll use that same equation we just used a couple minutes ago. Delta theta equals omega initial times time plus 1/2 alpha t squared. I know I've got 8 pi radians here. So 8 pi, I'm not even going to put the unit, I don't want to mussy it up a little bit. I know that my angular speed to start with was 0. It started from rest, so that whole thing cancels out. 1/2, it says it accelerates with 2 radians per second, t squared. These two cancel themselves out. So really, we're just looking at the square root of 8 pi as the time, which should equal 5.01 seconds. It's just kinematics. I know it looks a little bit different. We got to maybe convert the distances a little bit, makes a couple of conversions, but at the end of the day, it's no different. I will go through this problem. It's a little bit more involved. Similar setups, similar ideas, and the ideas are the most important part, let's be honest. So we've got a couple things going on, right? We've got these two forces of tension pulling upward, and then we've got a couple of masses right here in the middle. We've got that mass, and we've got this mass all pulling downwards. So we want to know how much tension does each of those ropes have to have so that, number one, we are not rotating at all, and number two, we're not actually moving up or down at all. And it's got this huge big setup, and it just wants us to find what those two tensions are so that we can hold it steady. So I'm going to start with net force. Net force equals ma. Because I want my acceleration linearly to be 0, my net force has to be 0. So my torque 1 plus my torque 2, because those are both upwards, has to be equal to the forces down caused by all of those different masses. 1200 times g, so we've got mg there, and another mg, and another mg, 1000 times 10. So what ends up happening is that T1 plus T2 must equal 30,000 newtons. So I'm going to sort of keep that little bit of information, and it'll help me out a little bit later. So now I need to balance all of my torques. And there's a trick that you can do when you've got these two sort of unknowns. What you do is you say, first, you're going to make this point, one of those sides, your axis of rotation, and balance out all the torques that way. So this force here does not exert a torque. Because it's right at that axis, it does not exert any torque, so I get to actually leave it out of my equation, which is nice. I don't want it there, to be perfectly honest. I want a net torque of 0 if this is the case. So that means that any torque that is clockwise has to be balanced by this other torque that is counterclockwise. So they all have to be equal. So my torque from the tension 2, so I've got my force times the distance away, so that is 16 meters. And for all of these, we are going to have 90-degree angles. We don't have to worry about the signs there. So torque 2 times 16 meters, that has to equal the weight of the 1,200 kilograms, so 12,000, times its distance from this point, just 3 meters, plus 800 times its distance from the left, which is 10 meters, plus, and it's 800 times 10 because it's the weight, plus 10,000, I've got 1,000 times 10, and I need the distance here. So for this object, because it's uniform, it's not different in different places, it will be directly in the middle is where that weight will really be. That's its center of mass. So that is actually 8 meters away from there. So I took each of the torques that were going counterclockwise, I set it equal to any torques that went clockwise, and when I solve all that algebra out, I end up with a tension, which is what I'm looking for, tension 2, of 12,250 newtons. So the trick to this problem was setting one of these tensions to be, one of the places there to be an axis of rotation. You can sort of get around having both of them in your equation. It's nice. You can solve for one exclusively that way. Now you could go back and you could reset and make this other tension your axis of rotation, or because you set this up top in the corner, the T1 plus T2 equals 30,000, that means that T1 is equal to 30,000 minus the 12,250 that we just calculated. And when you subtract it, you end up with a tension 1 of 17,750. I would expect a problem like that, maybe on a free response, could have a setup like that. for one of the big calculations. But what they might ask you to do instead is work with, instead of actually having numbers, it might be variables. It's tough, but you can do it. Other things they might do with this would say, well, if we moved some of these blocks, what would happen to the different tensions? If we move this block in or this block out, what would happen? Number 7, it has a star next to it because it's very important. An ice skater has a moment of inertia of 2.8 kilogram meters squared and is rotating with an angular velocity of 18 revolutions per minute. By pulling her arms, she reduces her moment of inertia. And the question is, what is her new rate of rotation? Rate of rotation is just angular velocity. Those are the same thing. So what we've got here is an ice skater with no forces acting on her from the outside. She's just bringing her arms in. And because of that, we know that the momentum at the beginning must be equal to the momentum at the end. So at the beginning, we had I initial times W or omega initial equals I final times omega final. And now it's just plugging in. 2.8 was her initial moment of inertia times an angular velocity of 18 revolutions per minute. That is equal to 0.7 times her new speed. Divide it all up, and you end up with 72 revolutions per minute. And that makes sense. It should be a bigger number, right? If we decrease our moment of inertia, that means that it's easier for us to spin. We spin faster. So if we decrease that, we have to increase the speed at which we rotate in order to keep that momentum the same. For B here, it is very similar, but this time it is using some variables. So we'll do it again. Again, the same setup, I naught equals omega naught equals I f omega f. So it says an ice skater is spinning. Her initial moment of inertia is 8I. And her final is just I. If her rotation rate at the beginning is 5 radians per second, what is WF? So if I divide both sides by I, we end up with 40 radians per second. Not too bad there. They are directly proportional. If I double one of the moments of inertia, I have to cut in half. I'm sorry, they're inversely proportional, moment of inertia and angular speed. If I double my moment of inertia, I have to cut in half my angular speed and vice versa. Cut in half my moment of inertia, I double my speed. Number 8, we've got a 50 kilogram adult standing on a free spinning disc, maybe like a merry-go-round, something along those lines. It's got a mass and a radius. Adult is standing at a particular place, and he has a tangential velocity of 5 meters per second as he's standing there. So it says, what is the angular speed of the disc? This problem is going to kind of take us through most of the concepts. So the first is going from tangential velocity into instead our angular velocity, and that's that R omega equals V equation. So the tangential velocity was 5. He was standing at a radius of 2 times that. So we end up with an omega of 2.5 radians per second. Not too bad. Moment of inertia of the disc person system. This is a calculation we don't have to do, but the answer is 575 kilograms per, meter squared. Big concept question here. The person moves so that they are standing in the exact center of the disc. What quantity remains constant for the entire system? Because there was no outside torque. Any forces or any torques that happened were from inside the system. That means that our angular momentum must have been conserved. That is a huge concept. I can't stress it enough. The more you get comfortable with that idea of conservation of angular momentum, or linear momentum for that matter, the better you'll do on this AP test. So it says, what is the angular speed of the disc after the person moves to the center? And that's another calculation involving this moment of inertia, but we will skip that. The new moment of inertia final is actually 375. So we set up L naught equals LF, and we've got 575, that's the moment of inertia, times the angular speed, the 2.5 radians per second, equals 375 after the person moved in, times omega F. Divided out, you end up with 3.83 radians per second. It should be bigger. If you move more mass closer to the center, you are going to have a lower moment of inertia, which we did. And the last, I've got a couple more problems. I got two more problems here. So a hollow sphere of mass m and radius r is at the top of an inclined plane. We talked about this problem, essentially. Which of the following pieces of information are necessary to find the velocity of the object at the bottom of the hill? That's a little different. We are going to need to know the height of the hill. That gives us mgh, really. And we also need to know how that mass is distributed in the sphere. The radius of the sphere doesn't really matter. We just need to know where the mass is in it. That is taken care of by the mass distribution. And the mass of the sphere doesn't matter. We've seen before that whenever we do these problems with, with energy, that the masses tend to cancel out. So the mass of the sphere does not actually matter in this case. So we're looking for an expression for the velocity v of the hollow sphere at the bottom of the hill in terms of the given quantities and fundamental constants. This is a derivation problem. This is an AP type problem. So at the top of the hill, we know we've got an energy of mgh, and that is initial. And because there's no non-conservative forces, our total mechanical energy at the beginning has to equal our total mechanical energy at the end. There are no other energies at the beginning, so I know that I've got to equal my energy at the end. In this case, when the object rolls down the hill, it will have some translational kinetic energy, right? It'll be moving side to side, but it will also be rolling. It is a sphere. It's going to roll down the hill, so I end up also having 1/2 I omega squared. So that's how we set it up to start with. We're just looking for an expression. We don't need necessarily any crazy values here. We don't need to plug anything in. All these masses are going to cancel out. It's not as clear though. And this is where we get into the fact that we don't need that I. That I ends up, there's a lot of breaking this down. I don't think they'll have something like this on the AP test now. I'm looking more at it. But more being able to realize that this is the setup for it. The I ends up getting broken down into, because of the shape of it, it is 2/3 mr squared. And then the values for the the angular velocity, that is v over r, and that's squared. So these r's actually cancel out, so that's why you don't need the radius of that. You can just have that. And that's why the masses end up all canceling out. It's a big mess. And again, I haven't seen any problems that deal with actually calculating that I or breaking that down into the mr squared or anything like that. So that might not actually be as accurate of a representation. What I would be more worried about is being able to just set up an equation like this and realizing that whatever energy I have at the top has to get split between both moving sideways and rotating. Objects that roll end up going down a hill slower than objects that can just slide. So now we've got a graph, and the nice thing about these graphs, and I haven't mentioned this yet actually, if you've stayed with me this long, this is your big payoff. Angular velocity in radians per second as a function of time. We can treat these graphs the exact same as we treat regular velocity time graphs. So it is asking for the angular acceleration. That is just the change in velocity over the change in time. But because we're talking about angular velocity, we've got sort of that omega. So it's the slope, right? It's the rise over the run. And it says for the first 0.15 seconds. So I would just get my slope of this line here, kind of draw a line of best fit. It looks like I go and I change my angular velocity by 12, so final minus initial, over the time difference, 0.15. And mathing that out, I end up with 80 radians per second squared. And that's for A, it's not for C. Through what angle in radians did the object rotate in the last 0.1 seconds? Well, this is a problem where we're looking for the angular displacement. For a regular velocity time graph, the integral was the displacement. So for an angular velocity versus time, the integral will just be the angular displacement, what it's looking for. So in this case, it looks like we've got a height of 12, and we've got a let's see, we've got a time of 0.1 seconds. So if we multiply those together, we should get 1.2 radians. And again, because our unit on the side on that y-axis was radians per second, we end up with an angular displacement also in units of radians. You could also do kinematics there. I think that's probably a little bit extra work. And my projector just turned off, so I'll just talk about this last one. I don't feel like turning it all the way back on. It says, how many rotations did it rotate during the entire process? Well, in this case, I would take the integral of all of this. Oh, I actually wanted to. So I would then take this integral, do 1/2 the base times the height. So that should be 0.15. So I already had the 1.2 from this other side, so I'll take 0.15 times the height of 12. And because it's a triangle, I got to divide that by 2. So 0.9 plus the 1.2, that gives me 2.1 radians, but I need to convert that into our revolutions. That's how many rotations actually occurred. So radians. So there are 2 pi radians per 1 rotation. So I need to divide that 2.1 by 2 pi, so divide by 2. And divide it, I don't think there's really a pi button here, so I'll just do 3.14. And we get 0.3343 rotations as we get in there. So I hope that was not too terribly bad. I hope that these videos have been helpful, at least make a little bit of sense. I know, again, I apologize we didn't get the chance to work through all of this during the school year. We just simply ran out of time. But hopefully this helps get you 1 or 2 extra multiple choice, maybe a free response, give you a shot at it. And if a couple people get a couple points better, then I did my job. So thank you all for listening, sticking with me for these 43 minutes worth. I hope this was helpful. Again, if you want more help with this, I would suggest the Khan Academy videos on rotational motion. They are very, very good. All right, everybody, have a good one. Good luck in your studies.